Hello once again, class, and welcome to another mock lecture. Today we're going to be tackling derivatives and the shapes of curves by way of, in some part, the mean value theorem, which gives birth to the derivative tests. We're still working our way towards this other application that we're trying to get to, which is optimization, right? We've done related rates. We want to get to optimization, which is analyzing minimums and maximums for real-world problems. But before we're able to do that, we should talk about what f prime and f double prime can tell us about the original function f. Now you might be thinking, haven't we done this before? Definitely. In fact, we came up with this thing. If you remember from a few videos ago, we talked about the relationship between a function, its derivative, and its second derivative. But the things that we did in that video is we were given stuff that looked like this. In this video, what we want to do is we want to be able to come up with that stuff. So instead of just being given a list of things and then saying, oh, okay, well, use this knowledge to make a graph, we want to be able to just straight up be given this instruction and then come up with a graph, kind of ourselves. Which means that we need to find intervals of increasing, decreasing, find extrema, find intervals of concavity, right? Find inflection points, find asymptotes, whether they're horizontal or vertical for non-polynomial type examples. And again, you might be thinking, we've done this mock, we've done all of these things, and that's true. Now we're kind of putting it all together. This is very much a let's put it all together and see what's going on sort of video. So we're going to start this endeavor by discussing a super important theorem, which actually is relatively intuitive. In fact, you might read it and be like, well, yeah, that makes sense. But the applications of these things are widespread and help us do a lot of super important stuff in calculus. It's called the mean value theorem. And what it says is that if f is a differentiable function on some closed interval a to b, then there exists a c value inside that interval such that the derivative at c is equal to the average rate of change for the entire function, right? That's what this is. This is average rate of change on this interval, is what that is. Another way to say this is, you could multiply both sides of this equation by b minus a. b minus a. That's terrible, but that says b minus a. It'll cancel on this side, and you're going to get this on the left and this on the right. That's another way that we could write the mean value theorem. And by the way, because it's differentiable on the closed interval a to b, it also means that it's continuous on a to b. Remember that differentiability implies continuity, but continuity doesn't imply differentiability. In this case, though, we're given that it's differentiable on this closed interval, and so then it must be continuous on that closed interval as well. But basically what it's saying is this, and I've drawn some random curve. We're looking at the closed interval a to b here, so we're only really looking at this part of the graph itself. And what I've drawn is the average rate of change. It's the slope of the line that goes between the endpoints on a to b. What the mean value theorem is saying is that at some point, c, inside that interval, the derivative, the slope at that point, the instantaneous rate of change, maybe is the best way to think about it in this case, is the same as the average rate of change on the entire interval. In this case, it actually happens at seemingly two locations, right? A c1 and a c2. In context, right, the analogy that I would make is, let's say that you drive a car 120 miles and you complete the drive in 2 hours, then the average speed that you're going is 60 miles per hour. But you're probably going like 40 miles per hour at some point. You're probably going 70 miles an hour at some point. What the mean value theorem says is that at some point during this 2-hour drive, if you look down at your speedometer, it must have read 60 miles per hour. That's all that this thing is saying. And what it allows us to do is prove that when the derivative is positive, that means that our base function is increasing. And when the derivative is negative, that means that our base function is decreasing. In fact, here's the proof of the decreasing one, if you want to pause and take a look at it. But if we take this knowledge and we add it to our knowledge of critical numbers, that's the main idea for today. We know what critical numbers are now. That's the sort of stuff that's going to help us find all of those things that we need to effectively graph a function, right? To figure out where its maximums and minimums are. And we can kind of apply even further. We can find with the second derivative in a sign analysis the intervals of concave up and concave down and all that sort of stuff. So we're joining this stuff that we learned from a few videos ago with the idea of critical numbers to basically find and place our own extrema by way of two derivative tests. And they're just named pretty succinctly first derivative test, and then the other one's called second derivative test. But the first derivative test says that suppose c is a critical number of some continuous function f, if f prime of x changes from positive to negative at this point c, meaning that it was above the x-axis before c and below the x-axis after c, then f of x has a local maximum at x is equal to c. So what I've drawn here is actually, this is f of x, right? That's what's going on. It's got a positive slope before c and a negative slope after, which means the derivative was positive before c and negative after. That implies that there's a local maximum. And the opposite is also true, the opposite behavior. If it's f prime is negative and then crosses the x-axis at c and then becomes positive, then there's a local minimum at c. If it doesn't change its sign, then f of x has no local extrema, and you're looking at kind of one of these situations, right? If you do a sign analysis on the first derivative, and you have, here's c, it goes from negative to negative, which would be a situation like this, then you just probably have some kind of an inflection point or something like that is happening. But the moral of the story is we can't conclude that there's a local extrema. In fact, the conclusion we can make is that there is no local extrema that's happening at c. So let's see this in practice. Let's do an example. Example 1 says graph v of x is equal to 3x to the fourth plus 4x cubed minus 12x squared plus 5. Okay, so the first thing I'm going to do is I'm going to find what are the intervals that this thing's increasing or decreasing, which means I got to find the critical numbers first. So I found the first derivative. I was able to even factor it. So I factored it into this thing nicely, which is ready for sign analysis stuff now. There's 3 factors for the derivative, 12x, x plus 2, and x minus 1. I went ahead and I plotted the critical numbers, which come, by the way, directly from these factors. X is equal to negative 2, for example, comes from this factor. 0 comes from this factor, and 1 comes from this factor, and that's why these critical numbers are here. And I found that v prime of x was negative on the interval negative infinity to negative 2, right, all this stuff, and from 0 to 1, and then it was positive from negative 2 to 0 and from 1 to positive infinity, and I went ahead and I listed those here, which means that we can see there's 2 minimums because the graph is changing, the derivative is changing from negative to positive in 2 locations, right, before and after 2 critical points, and there's 1 local maximum because the slope is changing from positive to negative at 1 of the critical points. So we essentially, by the first derivative test, we know that there are 2 local minimums, and to find them, I went ahead and I just plugged the critical points back into the function. Right, that's what all this function evaluation is. So I found there's a local min at negative 2, and that local min is negative 27, and then there's a local minimum at 1, and that local minimum value is 0. And then by way of plugging in 0 to v of x, I found that all these things went to 0, and so 5 was the local maximum value. Next, we need to figure out the intervals of concavity. So I found the second derivative. I determined that this thing factors into 12 and then 3x squared plus 2x minus 2, which I couldn't factor in a traditional sense, so I had to use some quadratic formula stuff to figure out where the zeros of the second derivative are, so that I could similarly perform a sign analysis. Because the sign is changing from positive to negative at negative 1.22, and then again from negative to positive at 0.55, we know that there's going to be some inflection points, right, that are happening for this thing. But first I went ahead and I recorded the concavity is positive, is concave up in this interval and in this interval, right, and that's what I listed here. And then it's concave down from negative 1.22 to 0.55, and that's what I've got here. But there are some inflection points because the second derivative is changing its sign at those values, and to place them on the graph, to put the inflection points somewhere, I plugged them back into v to figure out that, okay, well, negative 1.22 and approximately negative 13.5, and then 0.53 and approximately 2.31, those were my 2 inflection points for the graph. And so here we finally have produced a list of things that in a previous video we were just given, right? Now we actually know all the stuff and we came up with it, right? That's why this is very much a revisiting of this stuff, because now we were able to come up with the information that, again, we were previously given. But now that we know that information, we can go ahead and graph this thing. Okay, so first I put on my extrema. I knew there was a max at 0, 5, and there were two minimums at -2, -27, and 1, 0. So I went ahead and put those on there. By the way, notice that the Y scale is different than the X scale, so this thing is a little bit skewed, but I did that so that we could see the whole picture. Next, I placed the inflection points, and we know those are at -1.22, -13.5 approximately. That's this one, and then the other one was at 0.55 and 2.31. And then I just graphed this thing using the increasing, decreasing, and concavity intervals to figure out what this thing looks like. You'll notice at the inflection points, the concavity is indeed changing, and the graph is decreasing and increasing where it's supposed to according to where its intervals are. And we're able to graph this quartic function by just using calculus without the use of a graphing calculator. That's pretty cool. Now, granted, this is a polynomial. Non-polynomial things can get a little bit more complicated, but still, I think this is a great starting point. And by the way, I should mention that you might be wondering, how did I place these x-intercepts? You can still do that. You have to use synthetic division, which is the pre-calculus concept, which I'm not going to teach you here, but the point is we can do this with some other pre-calculus work. Now, you might be wondering, for absolutely no reason whatsoever, man, since we're having to take the second derivative anyway, wouldn't it be nice if we could sometimes bypass having to do a sign analysis to find extrema using the second derivative instead of the first derivative? Ladies and gentlemen, let me present to you the second derivative test. It says, suppose f double prime is continuous near C if f prime of C is equal to 0 and f double prime is greater than 0, meaning that its concavity is upwards, then f has a local minimum at C. In the other direction, again, if f prime of C is equal to 0, so the slope is 0, it's a critical number, basically is what that means, and f double prime of C is less than 0, meaning its concavity is downwards, then f has a local maximum. And if you stop to analyze that, this actually makes quite a bit of sense, right? The first, let's analyze this one, okay? What this is saying is that the slope is 0, right? So it's got a horizontal tangent line, but then also that particular tangent line is lying below the curve itself, meaning that its concavity is upwards. Well, the only way that you could draw something like that is if it was like this sort of situation, which is exactly what this says, right? The second derivative has to be greater than 0 because the graph sits above its tangent line, although I worded it confusingly because I said the tangent line sits below the curve, which is also true, but maybe the use of below, or maybe I should have just said the curve is above the tangent line instead, but it's the same thing. My point is, the only way that you could draw a situation where this happens would be something like this, and that is the very picture of a minimum. That's why there's a local minimum at that particular C value, right? That'd be C. So for our second example, let's consider Q of x, which is equal to x squared times e to the negative x. Okay, I want to produce a list of stuff that we could use to draw a graph. Although this one, there is a lot more going on, and so I really just want to focus on finding minimums and maximums. I'll still go through what the graph would look like, but it's not anything that I would expect us to be able to do kind of at this point. But, I'm not going to find a bunch of information and then not graph it. But anyway, let's consider this. I'm going to use the second derivative test to find the maximums and minimums for this one. But the first thing we need are critical numbers. That means I need to take the derivative, which I used the product rule to find, and then I have to set it equal to 0, and that's what this amount of work is. And I factored it into this, and you might be thinking, well, can't you also take out an x? And the answer is yes, but to make the second derivative easier to find, I actually just left it like this. What's important to note is that negative e to the negative x, that looks something like this. It's never 0, so you're never going to get anything that's 0. Which would mean that this part of it is the only piece that gives you something that's 0. So what I did is I said x squared minus 2x equal to 0. I factored out an x, and here's where I got my two critical numbers, 0 from this one and 2 from this one. Now, instead of doing a sign analysis, I went ahead and I did the second derivative test, right, to figure out where the maximums and minimums are. So I found the second derivative. Right, it was this, and again, I found it with product rule. I didn't label that, but again, product rule stuff happened here. Then I factored out an e to the negative x, which, would actually give me x squared minus 2x minus the quantity 2x minus 2 inside of this parentheses. And after doing some distribution and combining like terms, I got this. And then I plugged in my critical points, right? Because the second derivative test says when f prime of x is equal to 0, or c rather, is equal to 0, then we have to look at what f double prime of c is doing. It's either going to be greater than 0, or less than 0, or it could be 0, which is another case I'll talk about here in a second. But when I plugged in 0, I got that it was 2, which is greater than 0. And when I plugged in 2, I got that it was negative 0.27, which is less than 0. And so here we go. By way of second derivative test, we know that there's a local minimum at q of 0, which is 0. And we know there's a local maximum at q of 2, which is approximately 0.541. Okay, so let's go ahead and record that stuff. Now, if we want to get into graphing some stuff, then we would need to perform a sign analysis on the second derivative, because we're going to need to know what its concavity looks like. I went ahead and I put all three factors that are present here. I found the other two from using the quadratic formula. So really, q double prime of x, I'm kind of factoring into e to the negative x minus 0.59, again, approximately, and x minus 0.341, approximately. And those values just came from the quadratic formula. So I'm using the factor theorem to kind of write out the factored form. But in any case, here's the numbers that we're looking at where the sign is potentially going to change for q double prime. And a sign analysis is going to reveal that we get positive on the interval negative infinity to 0.59 and also 3.41 to positive infinity. And then it's negative from 0.59 to 3.41. Now I skipped a slide. This one, just again pointing out that this graph, now that there's no negative sign in front of it, it looks like this and is never negative. It's always positive. That's why I went ahead and filled out that row kind of automatically with a bunch of positives. But anyway, now we have where it's concave up and concave down. We can see that because the signs are changing in all three situations, then these are inflection points. And I went ahead and I calculated them by plugging them into Q. All right, and I found 0.19 is the output for 0.59 and 0.38 is the output for 3.41. Now, at this point, this is kind of where what we're able to do right now sort of stops. We actually can do more. Like we can find where the intervals of increasing and decreasing are with a sign analysis on the first derivative. I would argue that if you're going to have to do a sign analysis using the first derivative to see where it's increasing or decreasing, then there's no point in using the second derivative because you could just find the maximums and minimums here by doing a sign analysis on this. I didn't actually show the sign analysis, but this is where the function's increasing and decreasing, which you could kind of infer from where the local min and max is. But you have to be careful because the first and second derivative tests are not given to be biconditional, so you don't want to make any assumptions that you can't make. The thing that we can do, but not quite yet, is look for asymptotes. This particular graph has a domain of all real numbers, so we don't have to worry about vertical asymptote stuff, but there is a horizontal asymptote. It's one-sided. It requires using this thing called the L'Hopital's rule, which we don't know yet. You could actually probably do that with squeeze theorem too. I haven't looked into that, but I'm guessing that you could use squeeze theorem to figure that out. But in any case, there is a horizontal asymptote to the right, and that's what makes the graph look like this. That's why it's going over here like this. But again, I really just wanted to focus on using the second derivative test in this example to show that you can find local minimum and maximum based on the second derivative. You don't always have to go for a sign analysis or the first derivative test. But if you're graphing, I think I would probably just use the first derivative to find maximums and minimums anyway. You do have to be a little bit careful with the second derivative test though, because you'll notice the case that's missing here is when f double prime is actually 0. If it's 0, this test is inconclusive. I put fails kind of in quotation in that it fails to give us really any information at all. As a very quick example, if you consider the function x to the fourth, the first derivative is 4x cubed, so you find that there's a critical number at 0, and that's the only one. But when you go to check out what the second derivative is, you get 12x squared, and when you plug in 0, you get 0. So that case is not one of these things, right? It's both f prime and f double prime are 0, so we can't conclude anything. you'd have to use the first derivative's sign analysis to figure out that there actually is a minimum there. We don't get it from the second derivative test, though. We'd have to get it from the first derivative test, right, from using a sign analysis. So the second derivative test, while it can be very quick and have you bypass any kind of sign analysis, and again, this is really only a situation where you're finding extrema and you're not actually graphing. Because if you're actually graphing, then you should probably use first derivative test anyway, since you want to know where the intervals of increasing and decreasing are. But sometimes it fails. Sometimes we don't get the information that we're looking for, and then you'd end up having to use the first derivative test anyway. But that's it. Again, this lesson is very much a let's bring it all together. It was a chance to revisit how f prime and f double prime affect the graph of f in general. So yeah, now we know how to find all that stuff, and we can kind of put it all together to graph some stuff. Definitely polynomials. And even some non-polynomial stuff as well. So hopefully you guys learned something. If you have any questions, please leave a comment or send me an email. Thanks a ton for watching, and I'll see you in the next one.